Hello everyone, welcome to At Scale. I'm Thote, I'm a software engineer at Meta. I work for fault tolerance group within Meta. We are a group focused on making our services resilient to failures. Over 3 billion people use our services daily to connect with their loved ones and socialize with friends. Due to this scale, we get huge demand spikes during events like New Year or sporting events or events like COVID-19. Today, I and my colleague we are going to talk about how we manage to get capacity instantly to manage these demand spikes without having to provision use spare capacity in our fleet. Before we get into the details, let's look at high-level agenda for the day. First, I will start with why we needed to start the program. Later, we will discuss some of the challenges and the solutions that we came up with. And also, we'll talk about some of the specific challenges that we faced while scaling this program across our infrastructure. We also look at some of the learnings from using service degradation in one of our recent global outage. And I end with giving you some preview of ongoing service degradation work at Meta. Now let's look at why we needed to start this program. Early 2020, COVID-19 happened. Many countries announced lockdowns. These lockdowns had direct impact on our services and products. During lockdown, our application became even more critical for people who were not able to meet their loved ones in person. Lot of people spending more time on our services. We started to see unprecedented demand, up to 40% increase in demand for some of our services. At Meta, we build our own data centers. We forecast our hardware delivery to match the growth of our demand. But during COVID-19, our hardware supply was impacted due to lockdowns. Additionally, there was no clarity on when the capacity would arrive. So let's look at an example. So here is a chart showing our forecasted demand for one of our front-end service which serves Facebook users. So the yellow line shows how our actual demand deviated from our forecasted demand. So this led to a situation where our capacity supply stopped growing, but the demand started growing in an unprecedented rate. So our prediction showed that we needed significantly more capacity than what we forecasted to handle the situation. So we formed a working group to assess the situation and come up with mitigation strategy to manage the situation. Here are some of the action items that we take immediately. We stopped some of the new launches which would require more capacity, focused on improving efficiency rather than building new features. We also moved spare capacity to the services in need to serve critical use cases. Various teams demonstrated a lot of heroic effort to continue serve our users during this elevated demand situation. However, soon it was clear that the limit existed on how far we can push with these solutions. Additionally, these solutions possess low ROI after some point. But at the same time, our demand kept growing at unprecedented rate. We needed a more drastic and more scalable solution to manage this situation. So we started a new program called Service Degradation. The goal is to disable non-critical features to make room for critical features. Our product teams identified a lot of non-critical features and added control switches to control them during emergency situations. In the picture shown here, you might not see huge difference between the two screens, but there is a lot going on behind the scene. We have disabled badges, we are loading less number of stories, we are loading less number of comments and stuff like that, which will eventually help us get back extra capacity to continue serve the core use cases. But Facebook alone has 30 to 40 products. Managing these number of products with their control switches becomes infeasible in the long run. So we needed to build infrastructure to manage these and make sure that these knobs are available to use when it is required. So now let me hand over to my colleague E to talk about the challenges that we faced and how we overcome them to implement this infrastructure.
Thanks, Thote. My name's E. I'm a production engineer at Meta, and I am a member of the disaster recovery team. Before I talk about the challenges and solutions, let me start with the journey of Meta's service degradation program. Over the past decade, there have been a few attempts to implement service degradation at Meta. The first iteration of service degradation program goes as far back as 2009, followed by the second iteration in 2013 and the third iteration around 2016 to 2018. Overall, the idea has remained the same. We create a set of levers and switches which could be used to gracefully degrade users' experiences and in turn reduce the load on the servers. We can see from the timeline that every 3 to 4 years, service degradation program was needed and therefore was worked on as a temporary solution. After use, most of these levers became stale and stopped working over time due to lack of maintenance. Finally, in 2020, we restarted service degradation program. This time, we're committed to make sure that this program is well maintained and ready to use in the long run. Before implementing anything, we have identified 3 core values of a good service degradation tool. Service degradation as a disaster response tool should be trusted to function reliably when needed with ultra-low dependency. When activated, it should deliver the expected savings without causing any unexpected problems. And finally, although by nature it will degrade our services, we still aim to have minimal impact on users while producing intended savings. Now let's look at some of the challenges in the way. To summarize, we encountered 4 major categories of problems from our previous attempts. The first one is the number of products we have. Meta has a handful of major user-facing apps. Each of them contains a number of products. For example, Facebook alone has over 30 products, including ads, feed, marketplace, games, and more. All of them have many features and functions that can be individually switched on and off. On top of this, there are direct and indirect dependencies between them. The second challenge is our large and evolving code base. Move fast is one of Meta's values. Our engineers across the world continuously make changes to the code base. Performance of existing service change frequently and new features added. It is difficult to keep track of all of these and make adjustments to the levers and switches as well as expectations of savings. The third challenge is the cost of validation. In order to validate an emergency response tool, it must be tested in production environment with live traffic and real users. Given the nature of the service degradation program, it is inevitable that user experience as well as revenue will be affected when we execute such tests. And the last challenge is related to the cost of validation. Given the scale of impact on user experience as well as revenue, lengthy approval processes are often required before we can push this program forward. Now let me go through a few strategies that we use to deal with these challenges. We're inspired by the concept of Defense Readiness Condition, or DEFCON for short, from United States Armed Forces. DEFCON represents an alert state or level of readiness for defense. Each level has a predefined action plan targeting a specific situation. In our version of DEFCON, we use 4 levels instead of 5. These abstract levels help us simplify the control and configuration of service degradation switches and knobs. Here, level 4 represents business as usual, without any service degradation in progress. Level 3 to 1 represent low, medium, and maximum level of savings. On each level, we set clear expectations and use cases. For example, we switch to level 3 for small savings to deal with frequent and short-term demand spikes, like the New Year's Eve, Super Bowl. Level 2 is used to deal with medium to long-term capacity crunch, for example, a multi-region failure scenario. And finally, level 1 produces significant savings with considerable impact on users' experiences and revenue. It is only used to deal with once-in-a-lifetime events like the pandemic and rare global outage of Meta. Here is an example with concrete numbers for your reference. For Facebook, we target 5, 10, and 20% of CPU savings on level 3, 2, and 1 respectively. These targets are reviewed annually based on factors such as the growth of our infra and SLA. On level 3, there will be some visible but also very small impacts on user experiences. On level 2, some negative engagement impacts start to emerge when we throttle services for 10% CPU savings. And on level 1, we anticipate relatively significant user experience and revenue impacts as a trade-off for survival. Here I want to emphasize that at this level, we still ensure all core functionalities are operating as normal, like making posts and leaving comments. Users will notice limited features at this level, such as reduced search results and video contents in their feeds. To achieve and maintain these levels of savings, Facebook's service degradation program went through continuous testing and validation. We execute two types of tests. Number one, we design and conduct a weekly small-scale A/B test to get continuous signals and identify regressions as soon as possible. These signals come from system utilization metrics as well as user engagement metrics. With the help of our data scientists, we're able to test with a very small percentage of users and still get reasonably accurate estimates of impacts at full scale. However, we're not satisfied with theoretical estimates. At our scale, it is difficult to reason about the consequences of degradation without testing it in production. And it is hard to trust a tool in a real emergency situation without knowing that it has been tested in a similar environment. As a result, we also execute quarterly full-scale tests with 100% production traffic and users globally to validate the expected savings and identify side effects, cascading savings, or failures. With all the testing and validation, the next biggest task is to make a contingency plan. In an emergency situation, a contingency plan is required to save time in getting alignment and execution. We use A/B test and storm test results to help product teams understand the impact of their service degradation levels. We then define failure scenario-based usage policy for each level of degradation and get alignment and approval beforehand. Lastly, we create automated runbooks to take care of manual actions like notifying service on-calls, incident managers, and moving the service degradation levers and switches. Next, Thote will talk about how we scale our service degradation program at Meta.
Thanks, He. He explained how we went about solving service degradation for one of our front-end service, which serves our Facebook users. At the same time, other products like Instagram were also implemented similar service degradation solutions. And we realized that there are many critical services that would benefit from implementing service degradation. Along with managing load spikes, service degradation was also useful in many emergency situations like overload outages, where we use it to reduce the demand and avoid cascading failures. So we have decided to scale service degradation for all critical services, but we faced many new challenges in the process. Let's look at them. At Meta, we have few products with thousands of services, from a small service with 1 or 2 engineer teams to a large service with hundreds of engineers. These services are interconnected in complicated ways, and degrading one service, we can have unexpected impact on another service, and eventually on end users. Additionally, degradation mechanism will also change based on the kind of service. Most stateless services are CPU bound, storage services are memory bound, and we have quite a few services with network bound. Service degradation has to take care of these constraints to reduce the demand depending on the type of bottleneck. This is a very simplified view of how services are architected at Meta. We have a handful of front-end product services, then we have a set of platform services, and eventually generic backend services. Implementing degradation at front-end product services is relatively simple. We can easily identify non-critical user features to disable during emergency situations. But as we go down the stack, degrading generic backend services becomes challenging. Backend services may not have enough context to decide which feature to disable. Imagine a storage service with just put and get API. These requests can be coming from any features from any product. Even if they can be degraded, it can lead to an unexpected impact, like serving less cache requests will shift overload from cache service to the database. We can no longer make degradation decisions based on the state of the service alone. We need to take state of the entire infrastructure into consideration while making these decisions. Implementing degradation at product services is not only simple, but it is also very effective. Disabling features at this level will also reduce the demand on backend services, and this can be used to control overload on backend services. However, it is not very easy to operationalize this. For instance, when a cache service is overloaded, do we want to degrade Facebook app or Instagram app or both? Decisions like this involve a lot of alignment among product owners. As we mentioned before, the way we want to solve this is by designing a policy beforehand and have a approval from all stakeholders. So there is no one-size-fits-all solution to scale service degradation for all services. We followed federated model to scale service degradation. We empowered all service owners to implement their own service degradation program by providing necessary guidelines and infrastructure. We have decided to use 4-level model that he mentioned before for all services. These levels are based on the failure scenarios that they are designed to handle. This would help service owners to decide the degree of degradation needed for each level to manage the given failure. Along with service level A/B tests and full-scale tests that he mentioned, we also started to execute preemptive tests tailored for any upcoming failure scenarios whenever it is feasible to do so. These tests would trigger service degradation for all services at the same time to validate readiness of entire infrastructure. Also, we have built generic infrastructure required for services to implement and test their degradation program. A test platform to automate testing and run them on regular cadence, tools to measure impact of degradation on users and infrastructure, built a UI portal to see the status of service degradation for all services in one place. When we build emergency response tools like this, we will never know when they are going to be used in real scenarios. But we ended up using service degradation rather quickly in one of our global outages. The real-world usage provided an opportunity for us to see how the system worked and also helped us discover few challenges that were not obvious before. Let me hand over it to Yi to talk about this in more detail.
Now, let me tell you about our learnings from using our service degradation tool during a recent global outage. I'm sure you have guessed it. I'm referring to the outage on October 4th, 2021. This is a third-party plot showing the internet traffic of Meta services on that day. I'm using this as an approximation of demand. Here I would like to draw your attention to the recovery period of this outage towards the right of this graph. During the initial stage of recovery, there was a very steep rise in network traffic, indicating the quick recovery of Meta services. While this was a very good sign of more and more people regaining their access to Meta services, it had to be managed carefully for a couple of reasons. Number one, we knew that due to the outage, our internal job runners were scaled down and caches became cold. Such a surge in demand can create a lot of pressure on backend job handlers, caching services, and databases. We therefore wanted to prevent a surge that could cause another outage. Number two, a surge in computing resource demand would also create a surge in electricity usage in Meta's data centers, and we're talking about megawatts of power. This type of surge could have potentially caused problems to the power grid, and again, potentially leading to another outage. To manage these risks, we slowed down the growth of demand by activating service degradation. This highlighted period shows that the growth of demand significantly slowed down after service degradation tools were activated, which bought us time to ramp up the backend services more gradually. And finally, we disabled service degradation mechanisms and returned to BAU state. On the day, 4 user-facing apps and a few critical backend services activated their service degradation mechanisms to various levels. While we achieved desired reduction of demand, it required significant coordination among multiple teams when dealing with the outage. To summarize, we observed 2 significant challenges. Number 1, heterogeneous degradation techniques can have inconsistent savings and impacts. Most of the service degradation techniques maintain core services and reduce minor desirable services, while few of them randomly shed requests to reduce demand. They may have similar abstraction controls, but the actual savings and impacts are quite different. Number 2, ensuring effective communication and coordination. Communicating through a single channel to which all service teams subscribe to may help ensure centralized communication, coordinate decision-making, and that everyone is on the same page regarding when, where, and in what order to enable service degradation when a particular backend service is overloaded. Once decisions are made, it is then important to have a way to give good visibility to all the stakeholders. With these challenges in mind, Thote will talk about our future work.
As he explained, we have many kinds of service degradation techniques in our infrastructure. We can classify them into 3 major categories. First, service level degradations like disabling non-critical features. Second, shedding requests to reduce the load. We use this only to avoid outages. We can also delay the execution of requests by scheduling it to run at later times. Depending on the type of outage and the state of service, we need to decide which degradation techniques is effective. But as he also mentioned, it is challenging to make these decisions in real time by collaborating with all stakeholders in a middle of emergency situation. We have decided to make this experience seamless by building a centralized system with predefined and tested policies to execute during emergencies. To achieve this, we have started a new program called Unified Site Degradation. The goal of the program is to build a system to unify all degradation techniques under single abstraction. This system is designed to orchestrate various degradation techniques by selecting pre-approved policies based on state of the service, type of outage, and business priorities. Additionally, we also aim to make this self-executable by detecting these signals automatically. Another major focus area for fault tolerance is data center failures. There are many reasons for our data center failures like natural disaster, fiber cuts, power failures, etc. We already have a program to manage single data center failure without any impact on users. We do this by provisioning extra capacity for services to handle load when one data center goes down. For example, in this picture, you have 5 data centers. If you need to handle single data center failure, you need to have 20% spare capacity in each data center. Please note that this is a highly simplified view as there will be many other factors from hardware types to service placements which impact how we handle these failures. For the sake of simplicity, I will ignore them in this talk. When one region goes down, we move all the load to remaining data centers to continue serving our users without any impact. Now, you might ask what happens if 2 regions go down together. When we have fewer number of data centers, we can place them in different geographical zones to avoid them failing together. But let's look at what happens when data center count increases significantly. Now, let's increase the data center count to 10. We only need 10% spare capacity in each data center to handle single data center failure. But as we increase the number of data centers, it becomes hard to place them in different geographical zones due to various limiting factors like physical infrastructure, availability of talent, latency, etc. Increased number of data centers plus placing them relatively closer together will increase the chance of losing more than one data center together due to natural disasters or power failure. With our current approach, we need to provision more capacity to handle more than one data center failing together. In the example, with 10 data centers, we need to double the spare capacity on our fleet to manage 2 data centers failing together. At Meta, we do have aggressive plans to increase our data center count in the future. With increased number of data centers, we will also increase the number of data centers failing together. This can get really expensive as we need to keep huge portion of our fleet unused to manage these outages. Due to the recent supply chain constraint and growth of our user base, we are unable to procure enough capacity in the short term. So we have decided to change our buffer-based data center outage handling strategy to use service degradation. With this approach, every service in our infrastructure will degrade themselves directly or indirectly by disabling non-critical features to survive more than one data center failing together. In this example, let's say we keep 10% spare capacity to handle single region outage, but we also use service degradation to claim back the extra 10% capacity that needed to handle two region failing together. So we have decided to manage two data center outage using combination of service degradation and spare capacity. We are currently building unified site degradation and also solving two region data center outages using service degradation. Hopefully, we'll talk about these programs more in detail in the upcoming at-scale conferences. Before we end the talk, I thought it will be useful to summarize three high-level takeaways from our effort in service degradation. First one, though we built initial version of service degradation to manage load spikes, we quickly realized that it can be used in various emergency situations to reduce the load and avoid cascading failures. The second, testing service degradation in production or production-like environment was critical for us to gain confidence to use these tools during emergency situations. Third one, due to nature of our product offerings, we need to keep significant amount of spare capacity on our fleet to manage demand fluctuations. But service degradation provides a viable trade-off to ensure capacity buffer can be used effectively. Thank you.